Pavithra Sundar, and today I will be presenting a poster on understanding the feasibility of using citizen science photographs to estimate avian eye sizes. I'm pretty sure that all of us must have noticed how birds vocalize intensively at dawn. But have you ever wondered why different species start vocalizing at different times, even within the dawn chorus? This question puzzled us, and we decided to dig deeper into it. It turns out that the time at which species start vocalizing depends on the foraging profitability at low light conditions during dawn. And the ability to see and forage depends on eye size. Eye sizes are traditionally measured from museum specimens and mesnated live birds. However, obtaining eye size estimates using these techniques for an entire bird community is challenging. While there is a publicly available data set curated by Osprey and Ritland from museum specimens, it lacks data for quite a few species. Now, with the advent of citizen science initiatives such as eBird, there is an extensive database consisting of various media such as audio and photographs which are available for exploration. And thus, here we use citizen science collected photographs, specifically from Macaulay Library, to estimate avian eye sizes, to ultimately study the influence of eye size on the dawn chorus onset times of a tropical rainforest bird community from the Valparaiso Plateau of the Western Ghats. Here, we show our preliminary findings for 25 species for which we had comparable data from Osprey and Ritland. We firstly chose high quality side profile images for each of these 25 species and calculated their eye size, their bill length, and bill depth using the Fiji software. We then calibrated each of these eye size estimates using the bill measurements from Avonet Trade database and calculated an average eye size. We then selected 10 pictures for each species which had the least error ratios. Error ratios being calculated by comparing the bill ratios from the Avonetrate database and the bill ratios from the photographs. Since body size shows a wider variation than eye size, we first conducted a linear regression between the log of eye size estimates and measurements and log of body mass. Then we conducted a correlation analysis between the residuals of these linear regressions and found that there was a significant positive correlation between the relative eye size estimates derived from photographs and the relative eye size measurements derived from the museum specimens, that is Osprey and Ritland's data. Interestingly, if you zoom into the plot, you'll see that some of the frugivores, such as Asian emerald dove, golden fronted leafbird, and Asian quail, they have lower eye size, relative eye size measurements and relative eye size estimates, probably because their eye size and body size scale at the same rate. Whereas some of the insectivores, such as Asian brown flycatcher, gray-headed canary flycatcher, or common tailor bird, they are insectivores, which is why they can be expected to have larger eye sizes compared to their body size, so that they can forage for cryptic insects. Thirdly, some of the raptors, such as crested serpent eagle or crested goshawk, Brahmini kite, black kite, they're all scattered away from the line, probably because of three reasons. One, they have different bill morphologies. Two, the portion of eye available outside might be different compared to other species. And three, there simply weren't enough side profile high quality images that we could use to estimate eye size for some of these species. Plus, we cannot use this approach to estimate eye size of owls because they have forward facing eyes. Um, But overall, we showcase a reproducible and innovative approach to supplement systematic measurements and also show how citizen science collected photographs can propel research on bird behavior and physiological traits. With that, Thank you for your time and attention.